Hey folks, welcome to another episode on Clear My Paper. This is kind of a continuation video, part 2 on the previous video. In the last video, we were talking about inverse of a matrix more from an geometric standpoint. In this video, we'll continue the same story from an algebraic standpoint. Again, these are all more intuition videos. If your intention is to just clear your paper, you can skip these videos. But let's get going, okay? So I've kept all the text from the geometric standpoint just for reference in case we need to scroll up. But let's get into the algebraic part of that, okay? So let's understand from algebraic standpoint. Let's talk about conventional algebra, regular algebra, which we know from high school mathematics, elementary mathematics, the number system and stuff like that. Let's understand some of the concepts or do a quick recap. And then let's try to draw a parallel between the conventional algebra and the matrix algebra, which is what we have been doing all along. But in the context, in this video or in this episode, we will do more in the context of matrix inverse or inverse of a matrix. Okay, so let's dive in. Okay, so let's understand in the conventional algebra, what is the notion of having opposite effects? What does it mean? Like, how do you think about algebraic operations, addition, subtraction, and so on and so forth, and think about the opposite of that? For example, addition and subtraction have opposite effects on the same operation. For example, if you try to add 5 to some number, and if you want to have an opposite effect where you want to reset it, then you need to subtract 5 from the new number to get back to the original number. For example, you say 4 plus 5 is equal to 9, but I don't want 9, I want to get back to 4. Then I say 9 minus 5. Whatever number I've added, I'm subtracting it to get back my original number 4. That's what I'm trying to do, right? So in that case, addition and subtraction have an opposite effect. They balance out each other. Similarly, in conventional algebra, multiplication and division do the same thing, right? For example, if you multiply 4 by 5, it gives 20. But I want to get back to my original number 4, right? Then what I do is I take this new number 20 and I divide by 5. So this and this kind of balances out. That's what we do. So in that sense, in the sense of conventional algebra, these operations kind of inverse each other's effect. If I do addition and if an addition kind of inverses the operation of subtraction and vice versa. Similarly, multiplication and division both kind of inverse each other's operation or whatever effect they have. That's kind of the concept and notion in conventional algebra or in numbers in general. Similarly, there is a notion of no effect or status quo. You take any number 5 and multiply by 1. It does not change anything because in terms of multiplication and division, I mean, not in addition or subtraction. If you take a number and multiply by 1, and if you take a number and divide by 1, it does not change anything. Its answer is the same, no change. So it's a status quo, right? There's no change. That's another concept that we all know. So let's focus more on the concept of multiplication division. That's where the matrix algebra kind of differs, and then we'll talk about what is the difference and how things work in the world of matrix algebra. Okay, so in closing down on the multiplication and division in conventional algebra, what we saw is when the combined effect, for example, if I have 5 and if I multiply it by the reciprocal of 5, which is 1 by 5, the net answer is 1. Okay, this is another concept that we know in conventional algebra. When we multiply a number by its reciprocal, the answer is 1. And when you say 1, basically there's no change. You multiply, divide anything by 1, it does not change anything, right? So this and this kind of go in together with no change and stuff like that. And this will play a big role in the context of matrix algebra. And that's the reason, although it's very rudimentary, I just wanted to bring in so that we can apply that in the context of matrix algebra where it will be more prominent. So now let's apply the same set of logic and draw a parallel what it would mean in the world of matrix algebra for all of this. Okay, I'm taking the same sequence, okay? So this is matrix algebra now, and this is where we need to pay attention. So in matrix algebra, as far as the addition and subtraction goes, the concept remains the same. So you have two matrices, okay? And let's say you add them. Let's say you add A and you add B and you get C, which is a new matrix, okay? You get a C. And from C, I want to get back to A. So what I do is I take C and I subtract B, whatever is B matrix, I subtract the same matrix to get A, right? And this is what I get. That's what I do. So the concept is same. Similarly, with subtraction, I do the same thing. If I was subtracting instead of multiplication, addition here, let's say if I'm going to subtract over here, okay, and I want to have the opposite effect, then I add over here and get the same effect over here. Okay, that's what we do. And in the world of matrix algebra, the concept of no effect, where we saw multiplying by 1 or dividing by 1 does not change anything. Over here, the 1 will be replaced, the number 1 will be replaced by an identity matrix, identity square matrix, which is nothing but the diagonal elements are 1 and remaining are 0 in a 2 by 2, or it could be in 3 by 3, it could be like this. All the diagonal elements, which is the main diagonal, the backslash will be 1 and remaining will be 0. So if you take any matrix, okay, over here, let me remove this over here. So if I take any matrix, like in the number system, if I multiply by 1 or divide by 1, but let's take multiplication for now for a reason. If I multiply by 1, it does not do anything. For example, we have seen 5 multiplied by 1 does not have any change, it's still 5. Similarly, in the matrix algebra, if you take a matrix, let's say A, and multiply it with identity matrix, which we saw, it does not change anything, it still gives me A only, okay? It does not. So in that case, that's also good enough. So we have an equivalent. Instead of number, we have matrix, but the effect is still the same. But where it differs is over here, the concept of reciprocal, where we saw the last one over here, 5 into 1 by 5. That's where it kind of differs, okay? So what happens is, in matrix, right? When you multiply two matrices, let me make some space here. Let me just get rid of all these things. Just give me a second here so that we have more space. Okay, let's see. Okay, so what happens is, normally when you multiply matrices in matrix multiplication, so let's say I'm going to draw it over here. So whenever you multiply matrix over here, let's say like this way. So let's say this is A and this is say B, I'm multiplying, and both are say 2 by 2 matrices. Okay, we're talking about only square matrices here, and we have like this. Okay, so when I multiply A by B, okay, so what I'm doing is I'm taking this row and this column, and again this row and this column, and then I take this row and this column. So we know the typical matrix multiplication, which is the row column matrix algebra, which we do to get the final matrix. So that's the equivalent of matrix multiplication, which is equivalent to the algebraic multiplication, where we do a simple number. 4 into 5 is 20. Although in the algebraic, the order does not matter. 5 into 4 is equal to also 20. But in matrix, the order matters. That's a difference. But still, the concept exists. Is not equal to B by A. We know that order matters in the matrix. But still, the concept of multiplication still exists. The difference is in the concept of division. So far, you would have never seen something called as division of matrix anywhere, which is kind of interesting. We have all the algebraic operations or the equivalent of all the conventional algebraic operation, but we don't have anything on the division part of matrix in that true sense of division. But we have something which kind of fills that void in a different way. So we normally don't say matrix A divided by matrix B. Adding this does not exist in the world of matrix algebra, but it still exists in the world of numbers, where we say 5 by 2 or 5 by say 10 by 2, something of that sort. We still say that in the normal algebra. So what happens here? How do we think about that particular void? Okay, so the void is nothing but inverse of a matrix. From algebraic standpoint, you can forget the division in the true sense of how it is applied in the normal algebra, conventional algebra, the way we discussed over here, dividing or subtracting by 5 or something like that. You can forget that. But in the world of matrix algebra, I would not say the equivalent, but the void is filled by not by division by matrix, by something called as inverse of a matrix, which still has the same effect of the reciprocal effect that we saw here, where multiplication and division are kind of balancing each other over here, if you see. So the net effect of a matrix and its inverse will still be the same, but how it is done and what is the context, we'll see that. So that's what is interesting about inverse of a matrix and what it means. And last but not the least, we have seen n number of applications of inverse of a matrix, and it has a powerful meaning, which we'll see, and it really provides some amazing insights, which we'll see in this video and other videos also. Where does the inverse come into play, especially when we talk about singular matrix and non-singular, and finding solutions to simultaneous equations, which you would have seen already by now. So let's take some examples and apply the concept of inverse of a matrix in this context, where we're trying to understand what happens in a conventional algebra and what happens in the matrix algebra on the left hand side and the right hand side. Let's talk about that, taking some real-time examples. So in the conventional algebra, let's say there's an x missing here, sorry guys, okay. In the conventional algebra, let's say we're trying to find the value of x, and in the matrix algebra we're going to find the equivalent is going to be, we are going to find the value, or we are going to find the value of the matrix x, which is what it is, okay, a set of elements. So over here, let's go through the left side first, completely top to bottom, and then we'll try to draw a parallel between conventional and matrix. So in conventional algebra, if you see this, it is 2x is equal to 10, and we're trying to find the value of x. That's what we're asking. So what are we trying to do? Typical elementary steps. We divide both the sides, the left side and the right side, by the same number to just get rid of this x coefficient, in this case 2. So we divide both the sides by 2 so that we get the x. So that step. And in this step, in other words, what it means is whenever we divide any number, right, at the bottom, if I have to bring that number in the numerator, so normally if I say 2 implies that it's raised to the power 1. And if I want to bring it in the numerator, I need to say 2 negative 1. That's what we do, because we change that exponent, positive or negative, based on how we are trying to swap the numerator and denominator. That's what we do. So this 2 over here, I can very well represent as 2 to the power of negative 1. And this 2x remains as is, 2x equal to, and this 2 again I can represent as 2 to the negative power 1, and this 10 is as is. So I can definitely represent that. And I'm just trying to put brackets here for a reason, so that I can bring those 2 to the power negative 1, the first two terms together over here, and this is also kept separately. And we know 2 to the power negative 1 is nothing but 1 by 2 over here, the same thing. So 1 by 2 into 2, it's going to be 1. So I know this, right? But I'm just intentionally bringing it so that it makes sense when I draw a parallel in the matrix world. So 2 to the power minus 1, 2 is nothing but both are reciprocal of each other. The answer is going to be 1. And I have this x, which is still I'm going to find. And over here, I'm saying 2 to the power negative 1 and into 10. And I know that 2 to the power negative 1. And then what happens in this case, sorry about that. In this case, 1 does not have any meaning. You remember we said 1 is as good as no effect of anything, right? That's what we discussed. 1 is multiplying by 1 has no effect. We can just ignore it. That's what we discussed. So we remove that and we just say x is equal to 2 to the power negative 1 and 10. And 2 to the power negative 1 is dividing by 2, which we already know, right? When we, it's like dividing by 2 to the power plus 1, which is what is same. It's all the same thing. And the final answer is going to be 5. This is what we get. So normally when we execute this execution, or when we solve this equation, we don't go to this, but for a reason I've kept all this mumbo jumbo so that I can draw a parallel in the world of matrix algebra. So let's now take this example and see whatever we learned from a theoretical standpoint, how does it apply in the matrix world or in the matrix algebra. So what is the objective? We are going to use matrix algebra, and we are to kind of demonstrate the concept of inverse, matrix inverse, and we are going to find the value of matrix x. In this case, we are going to find the value of variable x. Over here, we are going to find the value of matrix x, which will be all in caps, right? We have denoted in caps. Okay. So let's say we have a given matrix. Instead of 2x is equal to 10, over here we have ax is equal to b. Okay. And since we know matrix division does not exist, this particular thing we don't need, no step needed, because division does not exist. Okay. Now let's come to this step. If you see here, the same thing, I'm bringing something to the numerator and giving it a negative power. The same thing I'm doing it. Although I can technically say divide both sides by a, but it does not have any meaning. But if you want to imagine this way for the time being, it's not mathematical meaningful because we don't have division of matrix. But if you want to draw a parallel like this, we can use this for the time being. Okay, very, very short-lived in your memory. And the effect of this is going to be the same over here, where I can bring the denominator to the numerator with a negative power. So I'm going to say 8 to the power minus 1 into a into x, and similarly a to the power negative 1 into b. And now I'm going to remove this because this is not true. I just kept it so that you can just understand intuitively where we are going, and this is more of a concept and not really existing, but all the rest of things are real, okay, over here. Now I've got it here, and the same way I'm going to club it. I'm going to put the brackets here on this and get the terms together, same thing that we did. And since we know the reciprocal of each of the metrics is 1, in this case also it's not going to be 1, but it's going to be identity matrix or unit matrix. So this I is a identity or a unit matrix, the same parallel that we draw. And multiplying by identity matrix or a unit matrix is more of a status quo. It does not change anything. So in the next step, this goes away. I don't have to fix it because there's nothing going on. And what remains is x, the unknown matrix, is equal to a to the power -1, and b, and a to the -1 is nothing but inverse of a matrix. We are inversing it. These numbers are reciprocal. In this case, we call it reciprocal, or it's kind of inversing. In the world of matrix, we call it inverse. And so we get x is equal to a inverse b. But what is the value of a inverse itself? If you remember, we have derived this formula in the previous episode or previous 2 episodes, where we are talking about adjoint of a matrix and inverse in the same episode. In that case, in that scenario, we had derived that inverse of a matrix, A inverse, is equal to 1 over determinant. This is the determinant part, determinant of the coefficient matrix, multiplied by adjoint. And adjoint is nothing but transpose of cofactors. And I don't get into the details, but you can check that other video, transpose of cofactors, right? And that's what A inverse is. So this kind of the intuition of where this particular things come from. Whenever we say that, hey, we want to find the inverse of a matrix, we start over here, x is equal to a to the power -1 and b, where a to the -1 is nothing but a inverse in the context of matrix algebra, kind of an equivalent drawn from here. And that still has a bigger, deeper meaning, because solving this is a problem by itself, finding the adjoint and matrix and all those things. So that's kind of the intuition where this formula is coming from an algebraic standpoint. And moving on, before we wrap up, another example that we draw here, if you remember, I took the reciprocal, right? 5 into 1 by 5 is equal to 1 in the world of conventional algebra. Going by that, that's called as reciprocal, or we can call inverse in the context of traditional algebra. On the right side, we are not going to call it reciprocal, we are going to call it inverse. What does it mean? 2 multiplied by 1 by 2 is equal to 1 by 2 into 2. It's just reciprocal. The answer is going to be 1. And this can be also expressed in this way, like I discussed. I can move the denominator to the numerator with a negative power, or vice versa. And its answer is still going to be the same. It does not do anything. Okay. Similarly, in the matrix world, I can take a matrix. Technically, I don't have the concept of dividing by matrix. So this does not exist. Also, I put it does not exist. But notionally, to draw a parallel to this, if I were to do this, this is what it means. From here, I can easily talk about this in the same way, a matrix and a matrix inverse. If I multiply them, or I can take a matrix inverse and multiply by the original matrix, the answer is going to be I, which is a unit matrix. In the algebraic case, we get numeric 1. Over here, we get identity matrix or unity matrix, which is nothing but a matrix where the diagonal elements are 1 and remaining are 0. That's what we get. Okay. And that's what the whole notion about this reciprocal matrix inverse is. So if we're going to just find the inverse of a matrix using this formula, we can find that. Or if you have 2 matrices and someone says that both are inverse of each other, okay, when you multiply them, regardless of whichever order you take, if they're truly inverse of each other, the final answer is going to be an identity matrix. That's a test of 2 matrices if they're inverse of each other. That's what pretty much it means. And this is a concept that will go into whether a matrix is a singular matrix or not. And that's the reason I wanted to just plant that seed over here. So that's what I wanted to kind of give you or accomplish in this video, to give you a sense of what it means by inverse of a matrix from an algebraic standpoint. And we have done a geometric standpoint also, and putting it back, both of them together, gives a nice perspective for all the guys or folks who are craving for intuition on what exactly it means. And summarizing the key learnings over here, there are just 3 points which you need to remember. Okay, what happened? Okay, what is acting goofy? Okay, sorry about that. Okay, so what is that? In geometric sense, inverse of a matrix, A inverse inverses or undoes the original transformation that we saw. There is a transformation, and if you talk about inverse of a matrix, the A inverse matrix kind of, I don't know why it's acting goofy, it inverses that. From algebraic standpoint, which is what we discuss in this video, multiplying a matrix A by its matrix inverse, which is kind of a reciprocal in the traditional algebra, or vice versa, gives you a unit matrix, which is what we saw here, right? A into A inverse or A inverse into A gives you identity matrix. And last but not the least, the matrix, the applications of matrix, which we already saw, we are doing it kind of this video after the fact, is those can be used to solve the concept of inverse of a matrix can be used to solve simultaneous equations using the matrix method, which we kind of discuss in detail, where we saw these equations where there are two matrices given, ax is equal to b, and then we get x is equal to a inverse into b, which is what we saw above, and the a inverse itself is nothing but 1 over the determinant. This is a determinant multiplied by adjoint a. That's the context. So the summary of this episode, all these 3 simple points, and then we'll talk about in the next episode kind of a related topic, which is a natural segue into knowing what is singular and what is not singular matrices, but this concept will help you there. Hopefully this was a good episode for you guys and good learning. I'll see you in the next episode. Till then, stay safe. I'll signing off from Clear My Paper.